Signal strength drops abruptly when you move from the living room into your kitchen. This isn't random interference or equipment failure. It is a predictable geometric consequence of how electromagnetic waves interact with matter at specific frequencies. After that first surprise, we can slow down and trace the mechanism behind the geometry of signal dead zones, why your kitchen blocks your connection from the first physical step, so the effect stops feeling mysterious and starts feeling engineered. We begin by defining a signal dead zone as any physical area where received signal strength falls below the functional threshold required for reliable data transmission. Imagine your router emitting concentric circles of diminishing intensity, much like ripples spreading across a pond after a stone is dropped. As these electromagnetic waves travel through walls and furniture, their amplitude decreases until they reach a point where devices can no longer decode the information. For example, if your smartphone requires at least -70 decibels to maintain a connection, any location measuring below that value becomes a dead zone regardless of proximity. This geometric boundary exists not because the signal disappears entirely, but because it drops beneath the operational limits of your receiver hardware. Pause 0.8 to understand why your kitchen blocks your connection. We must first define what a Wi-Fi signal actually is. Wi-Fi signals are radio frequency electromagnetic waves that propagate through space carrying energy from the router to your device. These waves consist of oscillating electric and magnetic fields that vibrate perpendicular to each other and to the direction of travel. Imagine a rope being shaken side to side. The wave moves forward while the rope moves up and down, illustrating this transverse motion. In electromagnetic radiation, both field components oscillate in phase quadrature, meaning they reach their peaks at different moments yet remain synchronized. This geometric arrangement allows energy to transfer efficiently through air without requiring a physical medium like sound waves do. When these fields encounter obstacles such as metal appliances or thick walls, the wave interaction changes fundamentally. The geometry of this propagation determines whether sufficient energy reaches your receiver to maintain a functional connection. Understanding this transverse field behavior sets the stage for examining how physical barriers disrupt the line of sight path. Pause 0.8 to understand why your kitchen blocks your connection. We must first examine the fundamental geometry of signal propagation. Radio frequency waves travel most efficiently along a direct line between the transmitter and the receiver without deviation. This principle is known as free space path loss, where signal strength diminishes predictably based solely on distance in an unobstructed environment. Imagine two scenarios, one where a straight ray connects your router to your phone, and another where that same ray strikes a wall before reaching the device. In the first case, the wave maintains its energy through geometric minimization of path length, whereas the second scenario introduces immediate attenuation upon contact with matter. The integrity of the signal depends entirely on whether this direct line remains clear or if it encounters intervening obstacles that disrupt the propagation vector. Pause 0.8 when electromagnetic waves encounter non-conductive materials like drywall or wood. The energy does not simply pass through unchanged. Instead, these dielectric substances contain molecular dipoles that attempt to align with the oscillating electric field of the signal. As the wave frequency increases, these molecules rotate back and forth rapidly against their internal frictional resistance. This mechanical motion converts a portion of the electromagnetic energy into thermal kinetic energy, effectively heating the material slightly. For instance, a microwave oven exploits this exact mechanism by using high-frequency waves to agitate water dipoles within food. In your home network, standard Wi-Fi signals undergo similar attenuation as they traverse walls composed of plaster and insulation. The result is a measurable reduction in signal amplitude that weakens the connection strength at the receiving device. Pause 0.8 The geometry of your kitchen creates dead zones primarily because water absorbs Wi-Fi signals with unusual efficiency. This absorption occurs due to the high dielectric constant inherent in water molecules themselves. Each water molecule acts as a tiny dipole, possessing distinct positive and negative poles that respond vigorously to oscillating electric fields. When a Wi-Fi signal passes through moist air or food, these polar molecules rotate rapidly to align with the changing field direction. This rotational motion converts electromagnetic energy directly into thermal kinetic energy, effectively dissipating the signal as heat. Consider how a microwave oven operates on the same principle by trapping water molecules in a resonant cavity to generate intense localized heating. In contrast, dry materials like wood or plastic lack this polar structure and allow signals to pass through with minimal attenuation. Understanding this molecular mechanism clarifies why dense food containers often block connectivity more effectively than empty air. Pause 0.8. When radio waves encounter a conductive material like the steel door of your oven or microwave, they do not simply pass through. Instead, the free electrons within the metal lattice respond immediately to the oscillating electric field of the incoming signal. This rapid electron movement generates surface currents that create an opposing electromagnetic field, which cancels the incident wave inside the material. Consequently, the energy is reflected back into the room rather than penetrating the appliance or passing through it. You can visualize this mechanism as a ray diagram, where incoming signal lines strike a solid metallic barrier and bounce away at an equal angle. This behavior stands in direct contrast to how water absorbs energy by converting wave motion into molecular vibration and heat. While water acts as a sink for your connection, metal acts as a mirror that redirects the signal elsewhere. Understanding this reflective property is essential before we examine how these redirected waves interact with other objects in the room. Pause 0.8. When your router sends a signal through the kitchen, that wave does not travel in a single straight line to your device. Instead, it encounters metallic surfaces like oven doors or refrigerator walls, which reflect portions of the energy back into the room. This creates multiple copies of the same signal traveling different distances before reaching your receiver at slightly different times. The physical principle governing this interaction is called superposition, where overlapping waves combine to form a new resultant pattern. If two wave peaks arrive simultaneously, they reinforce each other through constructive interference, creating a stronger local signal. However, if one peak meets another trough due to the time delay from reflection, they cancel out via destructive interference, leaving a dead zone. Imagine two identical ripples on water meeting, where one crystallines with a valley resulting in flat, calm water instead of motion. This temporal mismatch between direct and reflected paths causes the distortion you experience as dropped connections or slow speeds. Pause 0.8. When a signal wave encounters an obstacle like a kitchen wall, it does not simply stop at the edge. Instead, every point on the wavefront acts as a source of secondary spherical wavelets according to the Huygens-Fresnel principle. These wavelets propagate forward and interfere with each other to form a new curved wavefront that bends around the corner. The extent of this bending depends critically on the ratio between the wavelength and the size of the obstacle. Lower frequency signals have longer wavelengths, allowing them to diffract more effectively around large structures like walls. In contrast, higher frequency waves with shorter wavelengths tend to shadow behind obstacles rather than bend around them. This geometric behavior explains why your router's 2.4 GHz band often reaches rooms better than the 5 GHz band despite similar power output. Pause 0.8. The geometry of your kitchen creates specific dead zones because different radio frequencies interact with physical barriers in fundamentally distinct ways. We must examine the inverse relationship between frequency and wavelength to understand why 2.4 GHz signals often outperform 5 GHz bands inside enclosed spaces. Lower frequency waves possess longer wavelengths, which allows them to diffract around obstacles like walls and appliances more effectively than shorter high-frequency waves. For instance, a 2.4 GHz signal behaves like water flowing smoothly over a rock in a stream, maintaining coherence after passing through drywall or metal surfaces. Conversely, the 5 GHz band acts similarly to light reflecting off that same surface, losing significant energy upon encountering dense materials due to its shorter wavelength and reduced diffraction capability. This trade-off means Selecting the appropriate frequency band depends entirely on your specific layout and the density of obstacles between your router and device. Pause 0.8. The geometry of your kitchen affects signal strength not just through walls, but also through antenna alignment. Every radio wave carries a specific polarization direction determined by the transmitting antenna's physical orientation. Maximum power transfer occurs only when receiving antennas match this polarization vector field precisely. Consider two dipole antennas where one is vertical and the other horizontal, creating a 90-degree misalignment. This orthogonal configuration blocks nearly all signal energy regardless of distance or transmitter power output. Even slight angular deviations reduce coupling efficiency by converting usable wavefronts into reflected interference patterns. Understanding polarization constraints leads us to examine how router placement geometry further shapes signal distribution patterns. Pause 0.8. To understand why your kitchen blocks your connection, we must analyze the geometric relationship between the router and the obstacles within that space. Signal propagation relies on line-of-sight paths, where radio waves travel in straight lines until they encounter a barrier. When these waves strike dense materials like metal appliances or thick masonry walls at oblique angles, significant signal attenuation occurs due to reflection and absorption mechanisms. Consider a standard kitchen layout where the refrigerator acts as a large metallic shield directly between the router and your smartphone. Placing the router in a corner creates an obstruction angle that forces signals to diffract around corners rather than travel directly to the receiver. A top-down floor plan reveals that central positioning relative to the kitchen perimeter minimizes these critical obstruction angles for most devices. This geometric optimization ensures that the majority of signal paths encounter fewer high-density barriers before reaching their destination. By prioritizing spatial arrangement over raw power output, we establish a foundation for reliable connectivity within complex domestic environments. Pause 0.8. When physical barriers like concrete walls or metal appliances block your wireless signal, the solution involves active devices that extend coverage through regeneration rather than simple amplification. A repeater or mesh node operates by first receiving the incoming radio frequency transmission from the primary router using its internal antenna array. Upon reception, the device decodes the digital data packet and then reconstructs a fresh signal waveform to eliminate accumulated noise and attenuation artifacts. This regeneration process is critical because it prevents the degradation that occurs when signals are merely amplified without correction. The node then retransmits this clean signal on either the same or a different frequency channel depending on its configuration settings. Consider a kitchen scenario where a mesh node sits in the hallway to receive the router's signal and rebroadcast it directly into the room behind thick cabinetry. This creates an extended network topology where each active point serves as a regeneration station for data traveling between the source and your client device. Understanding this cycle of reception, reconstruction, and retransmission clarifies why strategic placement is essential for maintaining throughput across multiple hops. Pause 0.8. Signal dead zones arise from predictable physical interactions rather than random failure. Understanding wave behavior through matter allows systematic mitigation strategies.